In section 8.2, we discuss series. What do we mean when we express a number as an infinite decimal? So for instance, what does it mean to write pi when it's equal to the irrational number? Well, the convention behind our decimal notation is that any number can be written as an infinite sum. So here what it means is that pi is going to equal 3 plus, you see the 1 over here, that's 1 over 10, plus 4 is in the hundredth place, that'd be 4 over 10 squared. And then the third one is in the thousandths place, so it's 1 over 10 cubed, plus 5 over 10 to the fourth, plus 9 over 10 to the fifth, plus 2 over 10 to the sixth power, 6 over 10 to the seventh, 5 to 10 to the eighth, plus we can go on and on. And we can see that those three dots will indicate that the sum continues forever. And the more terms we add, the closer we get to the actual value of pi. Now, in general, if we try to add the terms of an infinite sequence, going from n is equal to 1 to infinity, then we would get an expression of the following form, which is our first definition. We would have a subscript 1, meaning the first term, plus the second term, plus the third term, all the way to the nth term. Now, then it would continue, because those three dots would then give us a definition in which we call this an infinite series or just a series. And it is denoted for short by the symbol, which is the summation. So we would have the summation where n is equal to 1 going to infinity, or we can say the sum of the series a subscript n. Now, does it make sense to talk about the sum of infinitely many terms? Well, it would be impossible to find a finite sum for this series where we have 1 plus 2 all the way to 5 plus to nth plus it continues. And it continues because if we start adding the terms, we get the cumulative sums 1, 3, 6, 10, 15, 21, and so on. And then after the nth term, we would get n times n plus 1 divided by 2, which becomes very large as n increases. However, if we start to add the terms of the series, then we would get 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus 1 over 32 plus 1 over 64. And the common theme that's happened in the denominator is you're taking 2 and raising it to a power of n. So this becomes 1 over 2 to the n. And then we would get 1/2, 3/4, 7/8, 15 over 16, 31 over 32, 63 over 64, which means we would take 1 and then subtract 1 over 2 to the nth power. Now, if we take a look at the table to the right, it shows that we add more and more terms. And these partial sums become closer and closer to 1. And in fact, by adding sufficiently many terms of this series, we can make the partial sums as close as we like to 1. So it's reasonable to say that the sum of this infinite series is 1, and to write as the following. We would say that here is the summation of this series, 1 over 2n, which is equal to 1 over 2 all the way to 1 over 2n, which eventually is going to equal 1. Now, we use a similar idea to determine whether or not a general series has a sum, and we consider partial sums. So we would take s subscript 1, which is equal to the first term. S subscript 2 is equal to the first term plus the second term. S subscript 3 is the first plus the second plus the third term. S subscript 4 is the first term plus the second term plus the third term plus the fourth term. So in general, S subscript n is going to equal the first plus the second plus the third term plus the nth term, which becomes a summation of I is equal to 1 to the n of a subscript I. Now these partial sums form a new sequence, which may or may not have a limit. So if a limit as n approaches infinity of that sequence, that new sequence equals s exists as a finite number, then as in the preceding example, we call it the sum of the infinite series a subscript n. So for definition number 2, if we're given a series a subscript n going from n is equal to 1 to infinity, then we would let s subscript n denote its nth partial sum. So s subscript n would be a1, the first term plus the second term plus the nth term. Now, if the sequence is convergent and the limit as n approaches infinity of s subscript n is equal to s exists as a real number, then the series a subscript n is called convergent, and we would write the following. The first term plus the second term plus the nth term, as we continue, is going to equal s, or the summation of that sequence going from n is equal to 1 to infinity is equal to s. And this number s is called the sum of the series. If the sequence is divergent, then the series is called divergent. Thus, the sum of a series is the limit of the sequence of partial sums. So when we write the summation of that sequence going from n is equal to 1 to infinity and it's equal to s, we mean that by adding sufficiently many terms of the series, we can get as close as we like to the number s. And so notice that the summation of that sequence is going to equal the limit as n approaches infinity of that summation of I is equal to 1 to n of a subscript I.